The first one we're going to do in Chapter 7 is number 39. This is a good problem because it incorporates pretty much all the stuff that we need to know to do problems in Chapter 7. So this is the setup. You got an inclined plane right here to a pulley on the top, and then it's just straight down. We have a rope connecting block M to a 2 kilogram weight, like hanging over the top. We have friction between the inclined plane and block M. These are the coefficients of static friction and kinetic friction. And when the questions were asked if, what is the minimum mass M that will stick and not slip? And B, if this minimum mass is nudged ever so slightly, it will start being pulled up the incline, what acceleration will it have? Okay, so we're going to do part A, where we're trying to find the minimum mass of block M so that it doesn't move. So what do we need? We need a free body diagram. So we're going to do a free body diagram. We're going to do 2 free body diagrams, one for each weight. So for block M, we're going to do a free body diagram. This is what we have. We have gravity, of course, mg. We have the rope pulling, which is tension. We have a normal force, perpendicular to the surface, and we have friction. In this case, the friction is static friction. I probably made that too big. Let's make that static friction, like that. Okay? Now, part 2, remember, first part you always do free body diagram, second part you make components. So we're going to do the same thing we do with all inclined planes. We're going to make this our axis, x and y. Whoops, dotted here. This is the y-axis going up like that. So we got to take the components of the gravity to get it on the axis. So this angle, remember, is theta between the y-axis and gravity. So this becomes, right here, mg cosine theta. And this is, up here, mg sine theta. So that makes a rectangle. All right, so we got mg sine theta and cosine theta, and I did not make my tension long enough because remember, this is in equilibrium because we want it to not move, so the tension has to equal the sum of those two. So I'm going to make my tension longer so that the length of that arrow is equal to those two arrows summed together. All right, so there's my free body diagram for block M. Now I'm going to do a free body diagram for our 2 kilogram block. And so it's going to have gravity, which is going to be 2 times g. I'm just going to call this block 2, which is 2 kilograms. And then it has tension. Now tension is going this way. Notice though, the tension here has to be the same length as the tension there, because they're connected. They also have to accelerate together. So, but this is very important. Very important. And so get this down. Pay attention, because this is the biggest mistake that ever happens. Notice that if we call this positive x going up, when block M is going up in a positive acceleration, which way is the 2 kilogram block going? It's going down. And so if it's going down, this is positive, this also has to be positive going down. You must keep your signs consistent because those are connected. So if this one has a positive acceleration, this one has to have a positive acceleration. If you don't, you're going to get in trouble. So what I usually do is I mark it. I say, okay, this is positive direction here. This is going to be positive direction here. And that becomes important when you do your F nets. Okay? All right, so just remember this, or I like to think of it as the coordinate system rotating. If you've ever done, in math classes, you'll work on rotating coordinate system. All you've done is taken your x-axis, and the x-axis follows the rope, so the x-axis is now pointing down. Okay? That's one way to think of it. So we're going to do an F net x for block M. And we got tension minus the friction force minus mg sine theta. Now for part A here, we don't want the block to be moving, so this is going to be equal to 0. So we're going to say 0 is equal to the tension minus mu sub s times the normal force minus mg sine theta. How do we get the normal force? Well, we have to do F net y. So I'm going to do that over here. F net y is going to be positive normal force minus mg cosine theta. This is 0 because it's not flying off of there. And so the normal force is equal to mg cosine theta. So I can write this down as 0 is equal to T, the tension, minus mu sub s times mg cosine theta minus mg sine theta. All right. Now I can't solve that because I don't know m and I don't know t. So I have two unknowns. But I can use this one over here and I can say, oh, here's F net x over here. You're like, he's calling it x, but it's in the y direction. Remember, I rotated my coordinates, so x is going down. So this is going to be 2g. It's really just mg, but I just put the 2 already in. Minus t. Notice this is positive, this is negative. Backwards from what we usually do. But that's because we have to make it consistent. This is also not moving, so 0 is equal to 2g minus t, or I can say t is equal to 2g. Then I can plug that t into here. I can say 0 is equal to 2g, right? And then notice I got to pull an m out of these two because I want to solve for this. So I'm going to pull this out and say minus m times mu sub g cosine theta minus g sine theta. I mean plus, because I pulled out a negative m. Careful with your signs, okay? All right. Then I'm going to solve this for m. So I'm going to move this whole term to the other side to make it positive. So this becomes m times mu, and this is mu sub s. I lost the s, sorry. Mu sub s g cosine theta plus g sine theta is equal to 2g. And I'm going to divide by all this. I'm going to get m is equal to 2g over mu sub s g cosine theta plus g sine theta. But notice I could pull a g out of these and it would cancel with this, so these g's all go away. So this actually ends up being just 2 over mu sub s, which I have, which is 0.8 times the cosine of 20 degrees. Sorry, 20 degrees plus the sine 20 degrees. And when I calculate that, that mass is 1.83 kilograms. Or with two sig figs, it's 1.8 kilograms. All right, that is the minimum mass it could have, meaning if it had less mass than that, the whole thing is going to start to move. This is when the static friction is at its maximum so that it balances the tension. Okay? If it had more mass, then it would stay there for a while until the mass got so big that this term was stronger than this, and then it would start sliding back the other way, and then the friction would flip around. So it would change everything. Okay? So that's the answer to part A. All right. I don't have enough board space to do part B and not erase this, so we've got to change this. So I'm going to get rid of all this for part B. So if you have to, stop the video, make sure you get all this down. All right, for part B, things change. So we've got to look at our free body diagram and see what changes here. So what happens is, in part B, is somebody nudges it so it starts to move, so the static friction changes to kinetic friction. So the only thing that changes in my free body diagram is this becomes kinetic friction. Okay? But because kinetic friction is smaller than the static friction, all of a sudden the tension is greater than those two, and that block starts to accelerate, which means that block accelerates. Okay? So free body diagram, what happens is This stays the same, but this reduces. Tension reduces. And so this is bigger than this. This starts to accelerate. This is still bigger than those two. They both are accelerating. All right. So we didn't have to, let me take this off. We didn't have to change much on a free body diagram. All I did was switch it to kinetic friction because we're still going the same direction. But it does change things massively in the problem because I'm going to put F net x is now going to be T minus the kinetic friction minus mg sine theta. You're like, oh, that's the same, except we switched static to kinetic. However, the biggest change is this. Now it's accelerating, so I don't put 0 in there. I have to put ma. So this is the mass times the acceleration is equal to T minus mu sub k times the normal force. Well, the normal force didn't change, so I'm just going to put that in, which is mg cosine theta minus mg sine theta. Okay. Now I want to solve this for the acceleration, but I don't know tension. So I got to get the tension for this one over here, but it's changed. So now I got F net x is going to be equal, remember I still have to go positive down. In fact, it's more important now. When it's a static situation, you can get away with it, but as soon as it's accelerating, you have to have it going the right way. 2g minus t, but this is going to be replaced with ma, but my m is 2, so this is going to be 2a is equal to 2g minus t. And then I'm going to solve this for t, so I'm going to move this over here and I'm going to subtract, it's going to be 2a is equal to 2g minus 2a, or t is equal to 2g minus 2a. Essentially I just swap those places. Now I can plug that back into here.